The section on soil mechanics per se has really two main ingredients. One is mechanics. And in fact, it is quite surprising when we see our courses, the large extent of mechanics that is built in the syllabus. The second part is actually the soil behavior and the soil response to mechanical excitations. So to put the whole section in perspective, we are going to start by recognizing the equations that we use in mechanics. You may remember the analysis of a beam. Equilibrium conditions tend to be enough for a simply supported beam, but when we have too many anchors or limitations to movement, then equilibrium equations are not enough. And we need to also consider compatibility equations, whereby we assume that points that are together will remain together throughout the deformation. In other words, that there will not be a significant failure in the system from the point of view of parts moving away from each other, like when a concrete block breaks apart. But equilibrium and compatibility equations, while they are enough to give us enough equations, they are in different dimensions. Some of them could be in forces or moments, while these ones are going to be in terms of deformations, meters. Therefore, we need to translate either the equilibrium equations in terms of deformations or the compatibility equations in terms of forces. And for that, we need to be able to translate one to the other through the material stiffness. And not only the material stiffness per se, but also the geometry of the system. And that is where constitutive equations come in. So those are the equations that we are going to use in mechanics. But then we recognize that when we load a soil under certain confinement, we apply a deviatoric load to a cylinder made of soil. Then at the beginning, it gives us this asymptote at the smallest strain, and it moves towards another asymptote at larger strains. Recognizing these two asymptotic behaviors is critical for engineering purposes. In other words, the details in between sometimes play a secondary role, but the asymptotes are very important. And so we're going to consider the behavior of soils in these two asymptotes at smaller strains. What are the deformation mechanisms? And they're all focused at the contact between particles, so we're going to review contact mechanics. And we are going to assume linear elasticity for that regime. Linear elasticity is fascinating. It's so elegant and so versatile. Above all, because in a linear elastic regime, we can apply successive loads in any sequence of events, and the sum of the cause will produce the sum of the effects. Superposition principle applies. And so it leads to a very elegant solution. You may remember Boussinesq or Mindlin for piles, etc. Now, for larger strains, this ability of the soil to resist shear is intimately related to its frictional strength, as is well captured in Coulomb from the 1776 Coulomb's equation. The maximum shear stress is proportional to the normal stress. And because the water doesn't take any load, it is all about effective stress, what is effectively carried by the skeleton. So a very important component here is that we're going to be talking about effective stresses, and that is really the characteristic or the concept that is probably at the heart of soil mechanics. It is really the most critical component, and in its simplicity, it can be very misleading. So we're going to cover that one in some detail, and I strongly encourage you to pay close attention and to analyze it yourself. Now, we should have said that when we were talking about equilibrium and we analyze equilibrium at a point, one of the important results is that the state of stress at the point in equilibrium in terms of shear and normal stress defines a circle, which we call the Mohr circle. Now, if the state of stress at the point is a circle and the Coulomb frictional behavior is a line in the tau sigma space, then the interaction between these two will tell us when the point is at failure. And one of the important consequences from that is that we will be able to conclude that because soils are frictional, they can take a limited amount of stress anisotropy. For a given confinement, you will be able to apply a maximum amount of deviatoric load. And that is the concept of limiting stress anisotropy in soil behavior. Now, another very important concept in mechanics that allow us to solve problems that involve large strains is the fact that we may not be able to reach the perfect solution, but we may come up with a reasonable upper bound and a reasonable lower bound so that we can bracket the actual solution. And from engineering point of view, this is so elegant. We don't need to know the truth, but we just need to come pretty close to constraining the potential values of the truth. And these are the upper bound and lower bound theorems, which are also known as the statically admissible and kinematically admissible solutions. As you see, from mechanics, now we have wonderful theories. And the small strain asymptote, theory of elasticity, linear elasticity allow us to apply superposition. And the large strain asymptote, now we can use plasticity and upper bound and lower bound solutions to constrain the possible solution to our problem. Now, while all this is basically mechanics, now we have to insert into all these mathematics or all these solutions, we have to insert the behavior of soils. From the point of view of stiffness, at small strains, is controlled by contact mechanics. And from the point of view of strength, at larger strains, is controlled by interparticle friction and rotation and dilations. Now, all this evolution in the behavior of soils can happen while the liquid inside the soil can escape or be pulled in to accommodate for expansions and contractions. However, if that doesn't happen because the rate of loading is much faster than the rate of pore pressure dissipation, we're going to create changes in pore fluid pressure, which means that we're going to change the effective stress. And so we need to understand the drain and undrained response of soils very well. Finally, we're going to conclude looking at what is happening inside the soil and the fabric, and we're going to benefit from wonderful developments in the last 50 years using discrete element methods. Not to dwell on discrete element methods per se, but to highlight the important lessons that we have learned understanding the macro-scale response as an emergent phenomena from particle scale processes. And there will be other implications that will evolve along this series of videos. For example, the implications of dilation on liquefaction, on the curvature of the failure line, and the possibility of localization affecting the actual measured behavior.